When we talk to an AI like ChatGPT, it feels like it just gets it. It understands what we mean, the subtle connections between ideas. But how? How does a machine actually understand meaning? Well, it's not magic, it's math. And today, we're going to pull back the curtain on the core concept that makes it all possible: embeddings.
Really think about that for a second. How does a machine, a bunch of code and silicon, know that a car and a bike are both things you use to get around, but a car and, a banana are totally different? The secret is all about translating our messy, complicated human language into a language that computers can actually work with.
So here's the first big idea you need to grasp. The AI creates something we can call a map of meaning. It takes every single word, or sentence, or even an image, and it gives it a very specific coordinate in this massive, multidimensional space. It literally turns abstract ideas into concrete points on a map that a machine can navigate.
And that coordinate, that point on the map, that's called an embedding. An embedding is basically just a long list of numbers. It's called a vector, and that list of numbers captures the very essence, the soul, of a piece of data. You can think of it like a numerical fingerprint for a word, encoding its meaning in a way a computer can finally understand.
Okay, so how does the machine decide which numbers to put in that list? It follows this really elegant, powerful idea from the linguist John Firth. You shall know a word by the company it keeps. By scanning billions and billions of sentences, the AI starts to see patterns. It learns that words like dog and cat tend to show up in the same kind of sentences, near words like pet, food, and house. That shared context is everything.
Now, if the idea of a vector still feels a little fuzzy, this is a perfect analogy. You use vectors all the time, with colors, right? Any color you can imagine can be represented with just 3 numbers, one for red, one for green, and one for blue. An embedding does the exact same thing for a word, but instead of just 3 numbers, it might use hundreds or even thousands to capture all the different shades of meaning. And on this giant map of meaning, there's one golden rule, the most important rule of all. Proximity equals similarity. The closer 2 of these number fingerprints are to each other, the more related their original words are. So dog and wolf will be super close neighbors. Dog and skyscraper, they're going to be on opposite sides of the map. This simple geometric idea is the secret sauce to how AI understands us. Now this is where it gets really, really cool. Because these vectors aren't just dots on a map. They capture relationships so precisely that you can actually start doing math with them. Yeah, math with words. Remember those hundreds of numbers or dimensions? Each one is kind of like a different feature that the AI uses to understand the world. We can't always put a neat label on them, but you can imagine it like this. For cow and tiger, the dimension for is it an animal is basically identical. But the dimension for is it domestic or is it a predator, well, those are polar opposites. This is how the AI gets such a nuanced understanding. And that brings us to maybe the most famous, most mind-blowing example in all of AI. If you take the vector for the word king and you subtract the vector for man, and then you add the vector for woman, the resulting vector you get is incredibly close to the vector for queen. Just think about that. The model has learned the abstract concepts of royalty and gender just by analyzing patterns in text. It's incredible. And this isn't just some one-off party trick. It works for all kinds of relationships. You can do it with capitals. Paris minus France plus Italy gets you Rome. You can do it with concepts. Summer minus hot plus cold lands you right next to winter. It even works for things like job titles. This is the real power of turning meaning into math. But it wasn't all perfect from the start. The early embedding models, they had a pretty big flaw. They were static. Each word got exactly one vector, one fingerprint, and that caused a huge problem for words that can mean different things in different situations. Just take the word table. In one sentence, it's about a grid of data in a spreadsheet. In a next, it's a piece of furniture in your kitchen. An early model would give table the exact same vector for both, totally missing the context, and that was a major roadblock. So the solution was a huge evolution, contextual embeddings. These are the kinds used by modern models like BERT and GPT. Instead of having a fixed dictionary, these models create a unique embedding for a word on the fly, based on the other words in the sentence. So the table in the Excel sentence gets a totally different vector than the table in the furniture sentence. Problem solved. Okay, so why does any of this matter to you? This isn't just cool computer science theory. This technology is secretly running a massive part of your digital world. You're using embeddings every single day, probably without even realizing it.
When you search Google for a concept, not just keywords, that's semantic search, and that's embeddings. When Netflix or Spotify recommends something you actually love, that's embeddings finding similar items. Chatbots, spam filters, language translation, they all rely on this map of meaning to understand the world and to understand you.
A really powerful modern example is a technique called RAG. It's how we give chatbots access to new information or a long-term memory. When you ask a question, the system first turns your question into a vector. Then it uses that vector to search a huge database of documents, also all vectors, to find the most relevant snippets of info. Finally, it feeds those snippets to the AI as context, so it can give you a super smart, factual answer.
But there's a fascinating and really important wrinkle in all of this. Where does this map of meaning actually come from? And what happens when that map isn't just a map of our language, but a map of us?
And this is the crucial point. Embeddings learn from us. They are trained on billions of pages of text from the internet, from books, text written by humans. And that means they don't just learn that a king is related to a queen. They also learn every other pattern, every association, and every stereotype that's present in all that human text.
And this isn't just a theory. Researchers can actually go into these models and measure these human-like biases inside the vectors themselves. And what they find is a pretty stark reflection of the data we gave the machine to learn from.
Just look at this data. One study found that in the model, the vector for nurse was mathematically much closer to female words, while architect and programmer were much closer to male words. Now, the AI isn't making a moral judgment here. It's just a mirror. It's simply reflecting the statistical patterns it found in the text it was trained on. It learned our historical stereotypes because they were baked into the data.
And here's what's really wild from a technical point of view. Sometimes, these models don't just reflect our biases. They can actually amplify them. One study found that a 33% difference in the training data linking women with cooking became a 68% assumption in the AI model. Because the AI's job is to find and strengthen patterns, it can grab onto an existing bias and make it even stronger.
So, this leaves us with a profound challenge, really. As we continue to build these incredibly powerful maps of meaning, the giant question we have to ask is this: how do we get an AI to learn the beautiful complexity of human language without also having it absorb all the historical biases and baggage that comes along with it? How do we build a machine that's helpful without just encoding a smarter version of our own flaws?